Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day everyone. Hi, Dr. Zuhair here, and this is for the course of EPF3110 Mass and Energy Balance. So we are moving to the next topic under the energy balance, and this time we are going to learn about the properties of pure substances. Imagine we are drinking a cup of iced coffee, let's say. From time to time, the ice will melt. So it will change the phase from solid to become liquid. And there are a lots of thermodynamics element happen that require us to get to know more details about it and to do calculation in order to measure the energy and so on. So that's why we need to know about the substance first before we can do all this kind of calculation related to the thermodynamics as well as the energy transfer and balances. So that's why here we are going to learn about the substance, and in the real industry the substance will not going to be in a pure form. It will be in a very complex mixture, but for the spirit of understanding the concept of doing the calculation, we are going to touch on the pure substance in order for us to get the understanding on how to do the basic calculation first before we can even extend our understanding for the more complicated or complex mixture. So what is the definition of a pure substance? Well, basically the key point is to have fixed chemical composition throughout. For example, water, helium, carbon dioxide, and so on. So the pure substance does not have to be a single chemical element. For instance, like water, H2O. It can be also in the form of mixture of various chemical elements or compounds, but it need to be homogeneous. For instance, like air. Our air consisted of a few gases such as oxygen, carbon dioxide, and helium, and so on. And it still can be considered as a pure substances because although it is a mixture, it is homogeneous. Okay, and a mixture of two or more phases of a pure substance is still a pure substance provided if the chemical compositions of all the phases is the same. Okay, so let's just start with the example 3.1 here. Okay, so this is considered as a pure substance because this is fully nitrogen, this is air. Air consisted of oxygen, carbon dioxide, and so on. And if we are, and this is in gas form, gas phase. Okay, what about if we have two phases? Can it still be considered as pure substance? Yes. You can see here, this is water in the form of liquid and the form of vapor. This mixture will still be considered as a pure substance because it still consisted of the same chemical composition, which is H2O. But for air, okay, as I mentioned here, air is considered as a pure substance in the gas form. However, when it turns to be in the liquid air, the composition of the chemical is not similar like when it is in the gas form, and this is due to the different condensing at different temperatures at a specific pressure. So the composition of air, the gas inside of air, and the composition of gas inside the composition of the liquid air will be different. So this is not considered, this mixture is not going to be considered as a pure substance. Yeah, so I really hope that you are going to understand this. The most important thing is to know that the chemical composition is fixed throughout regardless of how many phases that the substance has, and in the same time, if it is a mixture of a few components, it should be homogeneous. Okay, and when it's come to substance, as I give you example before about the ice coffee when the ice melting and so on. So every substance also will experience different phases. Okay, generally we have three main phases: solid, liquid, and gas phases, and all of these involve energy. So we are going to describe about each phase. Okay, starting from the solid. Okay, we can see here this is solid phase, in which you can see that the molecules are in a fixed position because of the intermolecular bond, which is the strongest among all of these phases. And with the existence of temperature, velocity of the molecules oscillating will be increased. Okay, at sufficient high temperature, intermolecular forces here will be overcome and group of molecule break away in, then this is called as the melting point. Okay, so from solid, if the temperature is enough to break down the intermolecular forces, it will turn into liquid. Okay, in terms of the liquid phase, the molecules no longer at a fixed position. It will be flowy and has a weaker intermolecular forces compared in solid. Okay, but it's still in a very close position with each other, but it's no longer in a fixed position, in which if we introduce more energy to it, the molecules will be vibrating more, and the molecules will be moving far apart from each other, and it will now move randomly, and molecules in the gas phase are at higher energy levels because we already provide some energy to this system, so that the molecules in the gas will have higher energy levels, hence must give out large amount of energy before it can be condensed or freeze. Okay, so we have a lot of energy that is going to make all these molecules to move around. So in order for us, if we want to change it back to the other phases, to the liquid and to the solid, what we need to do is to remove all of this energy. Now we know about the characteristic of pure substances, and also about what kind of phase that the substances can change from time to time. Now let us look into the phase change processes that involve with the pure substances. Okay, consider a process where a pure substances start as a solid. Okay, so it started as a solid here. This is a pure substance. Again, we are just focusing on the pure substances because this is the most simple model as to compare with the more complicated mixture. So it's easier for us to understand the fundamental understanding about the fundamental concept behind this, instead of using a more complicated or more complex mixture. Okay, so consider that the pure substance is in a solid form. Okay, so the pressure is P naught, and from this is from point A, and then we introduce Q, which is the heat. Okay, so from time to time, after we introduce heat, which is the energy, the solid will also some of the molecule will turn into liquid. So this is going to be a mixed phase of liquid and solid. Okay, but the pressure is still P naught, and then the volume increase. So now we know that the temperature and the volume increase due to the phase change. Okay, and then after that, after enough amount of heat introduced into the system, the pure substance will completely become compressed air. Compressed liquid. And when it comes to compressed liquid, this means that the liquid is just about to turn into vapor. Okay, so it's all in the liquid form already, but it's just about to turn into vapor. Okay, and after we increase the heat more, we introduce more heat, the substance will change into wet vapor or saturated liquid vapor mixture. So it's going to have some gas and liquid of the substance, and the volume will be increased more and temperature will increase more because it's the energy. And lastly, after high heat introduced into the system, the substance will completely turn into gas. And if the energy given, the heat given is too high, it will turn to become superheated vapor. So this is the phase changes process, the phase change processes of any kind of pure substance. And it will be best to be represented by a phase diagram. Okay, so you're going to see a lot of phase diagram after this, and I'm going to explain about this diagram. Okay, so here phase diagram is a plot of a system variable. Again, another system variable we have now T and also V that show condition at which the substance exists as a solid, liquid or gas phase. Okay, so here we start with TV diagram. What does it mean by TV diagram? This is mean that is temperature and this is volume. So that's why it is called TV diagram. So we're going to start with point 1. Okay, similar that is 1. Okay, from point 1 here, it is completely in the solid form. The pure substance was in solid form, but when we increase the temperature, increase more the temperature, it will go into the second phase, which is the mixture between solid and liquid. So this is the region where the solid and liquid phase of the pure substance will occur. Okay, and when we increase more the temperature, it will move to the next phase, which is the liquid phase. So this is the liquid phase where all the substance has been completely changed into liquid phase until this saturated liquid line. Okay, so the saturated liquid line indicate that this is the line where any additional heat will definitely change the liquid into gas. Yeah, so that's why after we introduce more of the temperature, the heat, we will go into this region, the dome region. And this dome region will be consisted of two phases, which is the liquid as well as the gas phase. Okay, so this is the dome. Okay, so this is number 4. Okay, so it is here. Okay, so after we increase more of the temperature, we will go to the other region, which is the gas region, in which more temperature if we introduce will produce superheated steam or superheated vapor. Okay, and for this one, this is a general what I would say a general TV diagram, in which it depends to what pressure that we maintaining in this for this type of phase change. As the pressure, let's say this is P naught, as the pressure increase, it is expected that this line will also increase. So I'm just going to draw another line like this, assuming that the pressure here, maybe this is 1 megapascal and this is 0.5 megapascal, up to when we increase it more, then the line will become higher. Okay, so maybe this is 10 megapascal, up to the point where the pressure will touch this critical point. Okay, where this critical point is defined as the point at which the saturated liquid here and the saturated vapor are identical. So it's not going to experience any liquid gas dome here, but instead from the saturated liquid it will change to the saturated uh, vapor instead. So this is the critical point, and it's also every pure substance has different critical point, and this is also depending to the TV diagram. This is depending to what substance that we are looking into. Okay, so different substance has different TV diagram. So it's also have the critical point where here we know what is the critical point for the temperature, vapor, and also the pressure. Okay, we also need to know the term that will be commonly used in the sense of determining the thermodynamic properties, including the compressed air, the saturated liquid, and so on, because this is something that you need to understand the definition behind all of this term, because otherwise you will get confused and you will get wrong data from the steam table. Okay, so that's why I'm going to explain to you about the definition of each term, so that you're going to get some more understanding and some view about all of this term. Okay, so based on the this PV diagram here, we can see here we have saturated vapor, saturated liquid, compressed liquid, superheated vapor, and so on. So what does it mean by all of this term? Okay, we start with the compressed liquid and the saturated liquid first. The compressed liquid or subcooled liquid is not about to vaporize. So any normal water, let's say, at 1 atm and 20 degrees C, this is what we call as the compressed liquid. Any normal liquid or water that we have in the tank or in our cup of mug, or any water that will not going to vaporize, that's we call as the compressed liquid. And if this water at 1 atm and 20 degrees Celsius is further heated up to 100 degrees Celsius, still liquid state, but it is now considered as the saturated liquid. Now, when we increase the water temperature up to 100 degrees C, it's still considered as liquid because it's still in liquid form. But now we are calling this liquid as the saturated liquid, in which by definition saturated liquid is a liquid is just about to vaporize. So you can see from figure 3.5 and 3.6 here, and this is a compressed liquid, and in which at 1 atm and 20 degrees C, this is just a normal water. Okay, but when increase the temperature to 100 degrees C, but it's still in the form of liquid, this is what we call as the saturated liquid. It's just about to turn into gas. Okay, so that's why we have this saturated liquid line, and then this is the line where the water, the liquid, will be just about to change to gas phase. Okay, so now we move to the other terms. It's about the saturated vapor and the superheated steam. Okay, so once the water, yeah, now it's in liquid, but after giving enough heat, it will change the phase of the liquid into gas, right? So once the boiling start, temperature stops rising. Okay, so it will remain at 100 degrees C. This is if the pressure is 1 atm, yeah, because different pressure will cause different boiling point. Okay, so temperature stop rising, hence constant, even though heat is added up to the system. So still this is 100 it will be maintained at 100 degrees C, but the process, the energy that had been provided to the system will change the molecules of the liquid to turn into vapor. Okay, so increase in the volume, and so it will definitely will increase in terms of the volume because now it's changed to gas. Okay, and decrease in the liquid level due to the liquid water changing to water vapor. At this state, there is an equilibrium between water in liquid state and water in vapor state. Okay, so the water in liquid state and water vapor, and that's why we call it as a saturated liquid vapor mixture. This is what we call as the state where it is the state consistent of the saturated liquid vapor mixture. So in this phase, this is in this under this dome area. Okay, after all the liquid has turned into vapor like this one, okay, and the vapor is just about to condense back to liquid, this is what we call as the saturated vapor. Now if the no more liquid can be changed into gas, and it's still 100 degrees C, but all the liquid had turned into gas, so all of these are in the vapor or gas phase, and any reduction of the energy or the heat will cause some condensation. So at this stage we call it as the saturated vapor. Okay, so from this TV diagram, this is here, yeah, this is based on the saturated vapor depending to the pressure. Okay, as I explained before, and this is what we call a saturated vapor. When okay, so when the saturated vapor is further heated up, but we still heated it up, yeah, we heat it up, and now because before this is maintained 100 degrees C, but the liquid oil has been changed to gas, if we heat up more, then the temperature will increase more, and the vapor inside this is what we call as the superheated vapor. So there's a difference between saturated vapor and superheated vapor. So if you were to refer this, this is what we call as superheated vapor. The temperature will keep rising. Okay, so this is the TV diagram again. Okay, so when we heat up the temperature will increase with this compressed liquid until to the point where this is the boiling point, where the temperature will remain while changing the phase from the liquid to gas up to the point where we call this as the saturated vapor point. Okay, and then after no more liquid can be changed into gas, further increment of temperature will produce gas that is considered as the superheated vapor. Okay, so that's the definition of the saturated compressed liquid, saturated vapor, and superheated vapor, superheated steam. Okay, temperature, saturation temperature, and saturation pressure. Okay, temperature at which water start boil depends on the pressure. Well, therefore, if the pressure is fixed, boiling temperature is also fixed. For instance, like we always say that boiling point of water is 100 degrees C. But this is not necessarily true, because this is referring to the atmospheric pressure of 1 atm. If we increase or decrease the pressure, the boiling point will be different. Okay, so for instance, at a given pressure, the temperature at which a pure substance change phase is called saturation temperature. Okay, so the term saturation temperature is the temperature in which a pure substance change phase. Okay, so it's also known as the boiling point, or now we have a more generic name of saturation temperature. For instance, like if at pressure of 101325 kilopascal, the T set, the saturation temperature is 99.97. But if at a given temperature, okay, for instance, like a given temperature, meanwhile, the pressure at which a pure substance can change phase is called the saturation pressure, P set. Okay, so if we fix the temperature, but you want to increase or decrease the pressure in which the pure substance can change phase is known as the saturation pressure. So let's just refer to this. When we increase the pressure, they say this is okay. This is in kilopascal. Okay, our atmospheric pressure is 101 kilopascal, right? So it should be around this. So it's going to be like this. So this is the T set, the boiling point or the saturation temperature, and this is the pressure, saturation pressure. Okay, so if we were to increase the pressure to, let's say, 400 kilopascal, the saturation temperature will also increase. Okay, so if you were to put anything in water in a condition where the pressure is higher at 400 kilopascal, let's say, we will need more energy to boil up the water. Yeah, in this case is will only going to be boiled up, the water will only going to turn into vapor if the temperature is increased up to 150 degrees C, and so on. And this is also can be referred to this table too, where this is just going to give you some understanding about how the phase change happen. And we are focusing on the pure substance, because this is just the simplest way to express, to understand the concept of the phase change for the thermodynamic calculation. In this case, most of the time we're just going to refer to water. Okay, so we need a lot of energy during the phase change, of course, and this is what we call as the latent heat. Okay, the energy that is needed to change the phase is known as the latent heat, in which the latent heat of fusion mean the amount of energy released during freezing. Okay, so the during freezing or needed during melting is either the change from liquid to water or water to liquid. This is what we call the latent heat of fusion. And the latent heat of vaporization is the energy released during the condensation or vaporization. So this is the phase of liquid to gas. Okay, so latent heat, both are latent heat. This is the latent heat of fusion, and this is the latent heat of vaporization. Now we move to the property diagram for phase change process. We already been introduced with TV diagram, temperature versus volume, in which this diagram will illustrate it how the phase change will occur for any pure substance. Okay, and I want to highlight again about the critical point here, in which the point where the saturated liquid in this region and the saturated vapor states are identical. Okay, so beyond this critical point, these two will be identical. Okay, and you can see here the increment of the pressure will also increase the line for this. At some point it will reach the critical point, and which after a specific pressure it will no longer produce the phase of saturated liquid and vapor region. And all the critical properties for the various substances are given in table A1. I'm going to explain a little bit more about the property table later, and this is very important because all this while researches have been done in order to investigate and calculate the critical point for each substances, its pure substances, and other property including enthalpy, entropy, internal energy, and so on, in which this is very useful that we can refer to in order for us to calculate our thermodynamic properties. And this is something that I'm going to explain a bit later. And you can hear the important thing is the saturated liquid line here, and the saturated vapor line, the superheated vapor region. This is the superheated vapor region. So all of this had been explained in terms of the term before. So I really hope that you can now try to imagine how this works. And this is, I mean, the typical pure substance such as water. What about if we change the phase diagram now from TV? Now we are playing with PV diagram. Okay, now pressure and volume. So we fix with the temperature, but the diagram is showing about the pressure and the volume. Okay, similar dome like this that we will obtain. However, we can say that we have some declination in terms of the trend if we were to it reduce the temperature. Okay, let's say T2 is bigger than T1. If we reduce the temperature from T2 to T1, you can see here it will have lesser saturated liquid line and saturated vapor line. Okay, so this is also a way to express the phase changes process for any pure substance by referring to the PV diagram now. And the other one is the PT diagram, and this is what we call as the phase diagram, in which now is referring to the pressure as well as the temperature. Okay, so this is a bit more interesting, where you can here we have 2 point. One is the triple point and one is critical point, and we have three region. One is solid, vapor and liquid region. Depending to the line, we have the sublimation line, we have the melting line, and we have the vaporization line. During the triple line is the combination of all the phases. At this point, all the substance will have all the phases: solid, liquid and vapor. If we reduce into the sublimation line, the solid will turn into vapor directly without changing into liquid. If we increase into the melting line, the solid will turn into liquid, and then the liquid will turn into vapor. So this is the critical point in which if the pressure is beyond this critical point, the liquid and the vapor will be identical. Okay, and we have some other line or alternative line for the melting line, in which this is substances that expand on freezing and substances that contract on freezing. What are the substances that expand on freezing? Such as water. Water will be expanded during freezing, right? And some other substance will contract on freezing. So we have two lines for the melting, but overall is going to be like this in terms of the PT diagram. This just want to illustrate it to you about how the phase change will occur. Okay, now this is the more important thing that I want to describe to you, and this is something related to what we are going to do in order for us to do the energy balance. Okay, it's about the property table. Okay, so what I mentioned before, all of this diagram has been prepared by researcher, and it's really complicated actually, because every pure substances have a different value, have different triple point, critical point, different property and so on. So in order for the to make us more convenient, the researchers have provide a property table in which all the relationship between the thermodynamic properties presented in the form, because otherwise it's going to be very complicated and it's going to be very confusing. So for us, for this course, we are most of the time just referring to the steam table, which means that we are just referring to water. We are not referring to other type of pure substance. We just going to focus on the water for the sake of this course, because it is the simplest way of understanding the and calculating the energy. Other substances are also presented in a similar manner, but we, in our case, we're just going to focus on water. For each substance, the thermodynamic property are listed in more than one table. It's going to have a lot of table. So I think some students, they have some tendency to make mistake in order to extract the information from the table, in which is really important for you to. That's why I elaborate to you every single term used, such as the saturated vapor, superheated vapor, the compressed liquid, and so on, so that you will be able to extract the right information from the table. And a separate table is prepared for each region, such as the superheated vapor, compressed liquid, and saturated mixture region. That's why it's very important for you to understand all of these terms, so that you're not going to select the wrong table. Okay, so what are the tables? Okay, so well, actually there are lots of table. I'm just going to show you now hold on for a second. This is the table, okay, where this is based on the table provided in the reference book textbook, and this is more or less is focusing for water, but we have a lot of other table actually, but for us we just going to use some of the table provided here, in which you can see here the table A up to 1 up to 34. Okay, and every table have different component and different information. Most of the time we just going to use table A4, A5, A6, because it's saturated water based on the temperature, saturated water based on pressure table, and also superheated water, and maybe compressed liquid water, and so on. And we also may be going to use A1 in order for us to find the critical point properties, okay, for the water. So this is how it will look like, the table. Okay, this is for table 1. So for all of these substance is have the critical point, the TC, the temperature, critical point, the pressure, and also the volume, as what been shown in the diagram. Okay, for this critical point, yeah, this is can be obtained based on this table. But I also to highlight to you, let's say in table A4, okay, this is saturated water. Okay, what do I mean by saturated water? Saturated water means that it's about to turn into vapor, right? Okay, that's the definition, saturated vapor. So we have the temperature here, and this is the pressure, the saturated pressure. Okay, so if a question give you specific temperature and specific saturated pressure, and ask about you the specific volume, internal energy, or enthalpy, we can just going to find all the uh, information here. Okay, even for here we have the saturated liquid and saturated vapor, and so on, which I'm going to explain a bit more later. So this is all the table that I'm going to give you, in which for the test and exam it will be provided. But the most important thing I think is to know how to extract the information, because it has a lot of information here. It's just up to you whether you will be able to know where to find the right information. And this steam table will not only mean for this course, but you will use it for other courses as well, such as the thermodynamic for chemical engineering, the chemical engineering, thermodynamics, and so on. You will definitely use this steam table again. Okay, so let's just go back to our slide. Okay, for instance, like in table A4, okay, so this is a saturated vapor based on temperature. Okay, so we have the temperature already listed here. If they say it's 45 degrees C, so you know at 45 degrees C the saturated pressure. Okay, what does it mean by saturated pressure and saturated temperature? Okay, so saturated pressure is the pressure in which the phase change will happen. Yeah. Okay, and then we have information such as specific volume, internal energy, enthalpy, and entropy. Okay, in the case for this course, we're not going to touch on entropy. Okay, so just leave this alone. But for other courses such as thermodynamic, you will definitely will calculate the entropy. Yeah, because this is more related to the second law of thermodynamic. In our case, we just going to focus on the first law of thermodynamics, which is about the energy conservation. Okay, so other property here are very important for you to understand, and for you to know how to extract all the information. Okay, so now we have F. Okay, what is the difference? Specific volume, F is referring if it's in a saturated liquid. Gas, G is referring to the saturated vapor. Okay, so it's depending to the question actually. If the question mention about liquid, then you need to use the saturated liquid. But if it is about the saturated vapor, you need to use saturated vapor here for 45 degrees Celsius. However, sometime you can see there is a FG, let's say this is for internal energy, okay, UF, UFG and UG. So this is for the saturated liquid, sorry, and this is for the saturated vapor. And for FG is the difference between the saturated vapor and saturated liquid. So it's just a matter of UFG is equal to UG minus UF, for instance like this one, okay. So 2 4 3 6.1 minus 188.43, then you're going to get the answer 2247.47. Okay, so something like this. This is the method of minusing, so it's not really a big deal, but in the same time you need to know where to use UF, UFG or UG. And one more thing to highlight here, all of these unit mean it is in kg. Yeah, when it comes to kg, all of this is a specific volume, this is a specific internal energy, and this is a specific enthalpy. It's not just an enthalpy, it's not just an internal energy, because it's on the unit of mass. Yeah, so that's why this is also very important. I'm going to show you in the example later, but this is very important for you to understand that when you get all the information from here, this is the value for the specific internal energy. If the question asks about the internal energy, what you need to do is to multiply with the mass, okay, so that we can cancel out the kg, because the internal energy unit is only in kilojoule, yeah, or enthalpy is in kilojoule but without kg. Well, I'm going to show you an example later. Okay, so what is enthalpy? Enthalpy, for the total enthalpy, for instance, like, yeah, okay, for the total enthalpy, this is something that you can get from the steam table here also. Total enthalpy H, the unit is in kilojoule, is the meter of internal energy plus P, pressure, and also volume. Okay, but for the specific enthalpy, okay, specific you can see here now is kilojoule per kg. Okay, is equals to U. You can see this is a small u, not a big U, so that means it's a specific internal energy, and also the P, pressure, is the same, but V is specific volume. So that's why it's very important for you be aware with the unit here, so that it's not going to mess up with your calculation. And you can see here, this is an energy and this is P times V, yeah, pressure times volume. Pressure times volume have the energy unit. You can see this is the conversion. Kilopascal meter cube will be equals to kilojoule, and so on. So this is also going to help you in order for you to do the calculation later, if you were to calculate the total enthalpy as well as the total energy later. Okay, and okay, this is I already explained before. HFG is the enthalpy. Okay, here this is the enthalpy of vaporization, or latent heat of vaporization. Okay, remember I already told you about latent heat of vaporization is the energy needed to change the liquid into gas. Okay, it represents the amount of energy needed to vaporize a unit of mass saturated liquid at a given temperature or pressure. So if I need any question asked about the energy or the latent heat of vaporization, it should be the HFG, not SF, not not have HG is about the HFG. So we need to also see how the question will ask that suitable for the enthalpy of vaporization. So in order for us to understand how the steam table should be used and how the calculation should be done, we now try one example here. This is example 12.1. A rigid tank contains 50 kg of saturated liquid water at 90 degrees C. So we have all of this information already. And the question asks, determine the pressure in the tank and the volume of the tank. So we want to know the pressure as well as the volume of the tank. So try to imagine that we have a rigid tank that contains saturated water. So this is water, but it is in the saturated liquid form. Yeah, that means that it's just about to turn into gas. Okay, and the other information that we have is it is the mass is 50 kg and the temperature given is 90 degrees C. So how can we determine what is the pressure for this tank and the volume of the tank? Okay, so now this is where it is it is important for us to refer to the steam table. Let's just go back to the steam table. Okay, so this is our steam table. If we go to the first page here, there are a lot of tables that have been provided. So based on the information that we have, we want to go for the saturated liquid water, right? So from here we can see that table 5 and table 4 have the saturated water, and one is based on the temperature and one is based on the pressure. And in our case, we already got the temperature, so we're just going to use the table A4. Okay, so now we move to table A4. Okay, so this is the saturated water based on temperature. So all the temperature had been given on the first line here. Okay, so I'm just going to increase, enlarge it. Okay, so the temperature that had been provided is 90 degrees C. So we have 90 degrees C. Okay, so temperature. So now we want to know what is the pressure there. So the pressure there should be here 70.183, and then we want to know the volume. Okay, because it is in liquid, not in the vapor yet, so this is the volume that we want to get. Okay, so these are the values that we need to write down for our answer. So we go back to answering the question here. So now, based on table A4, the P saturated is equals to 70.183 kilopascal. Okay, because the pressure here definitely is a saturated pressure, by considering this is a saturated liquid water, it's just about to turn into vapor, so definitely the pressure is also the saturated pressure. So this is the answer for the pressure. What about the volume? So we have the VF, the volume, the specific volume for the liquid is 0.001036 meter cubic per kg. So again, I would like to highlight that this is a specific volume, okay, because it has per kg here, but we just want to know what is the volume. So the volume will be equals to M, the mass here, multiplied by VF. So the mass is 50 kg multiplied by 0.001036 meter cubic kg. So we can cancel this, so that at the end we are going to get the volume of the tank, which is 0.0518 meter cubic. So this is the final answer for the pressure as well as the volume based on the info from table A4 that we had determined. Now we move to the next example, and this time a mass of 200 gram of saturated liquid water. Okay, again saturated water is completely vaporized at okay, so now it's completely vaporized, okay, at a constant pressure of 100 kilopascal. Okay, now instead of giving the temperature, it give us the pressure. Determine A, the volume change, and the amount of energy transferred to the water. So we start by drawing the PV diagram first. Okay, so this is a PV diagram. So this is the dome. Okay, so this is the line. It's going to be like this, and then this is the line for the saturated liquid line. This is for the line for the saturated gas line before it's going to go for the superheated steam. Okay, so the volume for the gas is going to be here. The volume for the total vapor change will be here. Okay, so we want to know what is the volume change here. So it's Vg minus Vf. Yeah, V minus Gf. So how to get these two things here? We can go back to the steam table. And now instead of going to table A4, because this is based on the temperature, we go to A5. Because now it's a pressure. It's about pressure, okay? So it's already give you the pressure of it is 100 kilopascal, okay? So we now go to 100 kilopascal. So this is 100 kilopascal. Okay, and we want to know what is the volume, the Vg and Vf. Okay, so these two are the info that we want. Okay, so now we move again here. Okay, so V, okay, based on the table we know that Vg is 196,941 minus 0.01643, and oh sorry, this is not the, this is VGF, okay, VFG, okay, and then we are going to get the VFG is 1.6931 meter cubic per kg. Why this is not the change of volume? Because we still have this kg, in which in order for us to find the volume, we still need to multiply with the mass, VFG. Okay, so the mass is 200 gram, which is equal to 0.2 kg multiplied by 16931 meter cubic per kg. So we can cancel these two. At the end, the volume that we can obtain is 0.3386 meter cubic. So this is the volume change for A. This is the answer based on the data that we obtained from the steam table. Okay, for what about the B? The amount of energy transferred to the water. What does it mean by energy transferred to the water to vaporize it? So if you refer back to the enthalpy definition, enthalpy, H, enthalpy, the amount of energy needed to vaporize. Okay, so that's mine. Enthalpy is the one that we want to find, the amount, the energy that is needed to vaporize a unit mass saturated liquid at a given temperature and pressure. Okay, so the question is asking about the enthalpy. So what we're going to do, we are going to find in the steam table 2 what is the enthalpy. Okay, so this is the enthalpy of it, and because this is a and similar like specific volume, because specific volume does not have the VFG, but for the enthalpy we already have the HFG, so we're just going to get this. So this is the enthalpy that we want. Okay, so that's why it's very important for you to know what is the value that you need to find the steam table, because there's so many numbers here. You need to know which one is the right one for you to choose to answer the question. Okay, in this case it's asking about the energy needed to change from the from liquid to gas, so that's why we choose the enthalpy of HFG. So for B, we got the HFG is equals to 2257.5 kilojoule per kg. But will they be enough to say that this is the energy transferred to the water? No, this is a specific enthalpy, and we just want to get the just want to know the enthalpy. That's me want to know the H, which is in joule or kilojoule unit, no kg. So what we need to do, similar like the volume, we need to multiply with mass. So the mass is 0.2 kg, enthalpy is 2257.5 kg. Sorry. So at the end, you're going to get the final answer of 451.5 kilojoule. So this is the energy needed to completely vaporize the saturated liquid water. So you can see here the importance of referring to the property table, or most of the time we're just going to go for steam table to get all the data here, VF, SFG, and so on. I really hope that by doing so, that's the end of the class for today, and I really hope that you are going to get understanding about the concept behind the pure substance and the phase change, and what are the related calculation involved, especially when it comes to the property of the property table and the steam table, in which is really going to help you in order for you to calculate the energy needed. Okay, because we are going to move forward for the energy balance. Okay, so in order for you to calculate the energy here, you need to know about the property of the pure substance, including the one that you will find in the property table, because for thermodynamic property is really complicated. It cannot be represented by just a single formula that you can just put values and you get the answer, because it's very complex. So that's why we provide some properties in terms of the table for you to refer to, and in depending to which phase and which situation. So but it's very important for you to know how to get the right information from right table, because otherwise it's going to affect the whole calculation. So that's all. I really hope that instead of just doing these two examples, you also going to find other example related to the steam table, the property table, and so on, in order to familiarize yourself with the uses of the table. Thank you. Bye bye. Assalamualaikum.